Section: Introduction. In this section, we discuss how, over the past year, the creation of images from text descriptions using diffusion models has made significant strides. This includes everything from creating lifelike portraits to fantastical creatures. A particular area of interest has been in making these models more personal. This means taking a model that can already turn text into images and teaching it to include specific things that a user likes, such as their pets or a new houseplant, in the images it creates. For example, imagine having a picture of your pet sitting in Times Square at night. This kind of customization is a big step forward because it lets users have more say in the images that are created, opening up new possibilities for how these models can be used. However, we've noticed some challenges, especially when trying to include multiple personal items in one image and making sure the image accurately reflects the text description. For instance, if the model is trying to show both a dog and a cat in the same picture, it might struggle because it can't always tell the difference between the two. We think this problem comes from the way these models were originally trained. They often learn from datasets where each picture usually focuses on one thing, and the description is quite general. This makes it hard for the model to handle more complex scenes where multiple items need to be shown together, especially if those items are quite similar to each other. To tackle this, we decided to try a different approach from the usual model improvements. We focused on making a better dataset that has pictures and descriptions of scenes with multiple items. We used the latest technology to create realistic images that combine several items a user might provide, along with detailed descriptions of these scenes. We call this new approach Gen4Gen. We also worked on making the descriptions better match the images by using what's known as prompt engineering. This helped us create over 10,000 images for a new dataset we named MyCanvas. We realized that to truly measure how well our approach works, we needed a good way to evaluate it. Most current methods either look at how well a model can create images in general or how well it can handle a few personalized items, often relying on what people think of the results. So, we came up with two new ways to measure success, focusing on how well the images match the descriptions and how accurately they include personalized items. Our experiments showed that by using our new dataset and these measures, we could significantly improve the ability to create realistic images that include multiple personalized items, even in complex scenes. This success suggests that our method of creating better datasets could be a powerful tool for improving image generation models in the future. In summary, our work contributes to three main areas: the importance of using advanced models to create high-quality datasets, the impact of dataset quality on personalizing images with multiple concepts, and the need for a comprehensive way to evaluate these personalized images. We hope our dataset, MyCanvas, along with our new evaluation methods, will help advance the field of personalized image generation. Section Summary. In this section, we observe a significant advancement in text-to-image diffusion models, particularly in personalizing generative models by incorporating user-provided concept images to create tailored scenes. Our approach, Gen4Gen, focuses on improving dataset quality for multi-concept personalization, leading to better image-text alignment and composition accuracy. By introducing the MyCanvas dataset and carbon monophosphide clip and TI clip scores, we aim to provide a benchmark for evaluating multi-concept personalization methods, emphasizing the importance of dataset quality and holistic evaluation metrics in advancing AI foundation models. Section: Gen4Gen, a data-driven approach to multi-concept personalization. In this section, we introduce Gen4Gen, our innovative approach designed to enhance the personalization of images that incorporate multiple concepts, such as combining images of a dog and a houseplant into a single, coherent picture. Our method focuses on improving the quality of data used during the training process, which, as we've discovered, significantly boosts the quality of the generated images that feature multiple personalized concepts. This is a departure from previous efforts that mainly concentrated on refining training strategies. We start by discussing the principles behind designing our dataset. We noticed that images from the most aesthetically pleasing subset of the LAION dataset often had complex visuals that were poorly described by overly simplistic or inaccurate text descriptions. This discrepancy, along with issues like low-resolution images containing multiple objects, inspired us to establish 3 key principles for our dataset design. First, we ensure that each image is paired with a detailed text description that accurately reflects both the foreground and background objects. Second, we focus on creating images where the object's layout and the background are realistic, avoiding artificial-looking compositions. Lastly, we prioritize high resolution to ensure the generation of high-quality, multi-concept personalized images. Our Gen4Gen creation pipeline is then detailed, consisting of 3 main stages: object association and foreground segmentation, LLM-guided object composition, and background repainting and image recaptioning. Initially, we select a set of objects that are likely to coexist in real life and obtain images representing these objects from various sources. We then use a category-free saliency object detector to segment the foreground of these images. Despite the challenges posed by artifacts in current models, we aim to provide a comprehensive benchmark for understanding these models' capabilities in complex image generation, incorporating human oversight for quality control. In the second stage, we leverage the zero-shot capabilities of large language models, LLMs, to determine a probable set of bounding boxes for object composition. By showing a few examples to ChatGPT and asking for bounding box suggestions based on these objects, we can compose images with realistically scaled objects placed in appropriate locations. This step occasionally requires adjustments to ensure the object sizes are realistic relative to each other, for which we consult GPT-4. For the final stage, we generate backgrounds that blend seamlessly with the foreground objects. Instead of relying solely on text-to-image diffusion models, which can produce unpredictable results, we start with a high-resolution background image that matches a given prompt. We then repaint this background using a diffusion model, ensuring a smooth integration of the foreground objects into the scene. This process is enhanced by using a soft mask for the objects, which results in a more natural-looking image. To complete our dataset, we recaption the final images using multimodal large language models, MLLMs, to generate detailed descriptions that closely follow the visual content. This step involves feeding the images into LLAVA 1.5 with specific instructions to describe the scene in detail, adhering to a word limit that matches CLIP's token constraints. This recaptioning process enriches our dataset with diverse text descriptions that accurately reflect the image's content. By repeating these steps for various combinations of objects, we compile a comprehensive dataset, MyCanvas, which serves as a benchmark for evaluating the capabilities of current models in generating high-quality, multi-concept personalized images. Examples from our dataset are showcased to illustrate the effectiveness of our approach. Section Summary. In this section, we introduce our approach to multi-concept personalization, aiming to generate new images containing multiple user-provided concepts with varying backgrounds. We focus on enhancing data quality during training to improve the generation quality of these personalized images. Our dataset design principles emphasize detailed text-image alignment, reasonable object layout, and high resolution to ensure high-quality image synthesis. The Gen4Gen pipeline involves stages such as object association, foreground segmentation, LLM-guided object composition, and background repainting, with human involvement for data cleaning to create a benchmark for complex image generation tasks. Section: Dataset Statistics. In this section, we discuss the dataset statistics for our MyCanvas dataset. We gathered 150 objects, some represented by a single image and others by multiple images. We then created 41 probable compositions, which we refer to as a set of objects, and initially had over 10,000 images. After a manual review for the best repainting results, we narrowed it down to 2,684 high-quality images. The statistics of our MyCanvas dataset show that the average length of words per caption is 17.7, with about 30% of these captions having more than 20 words, each word carefully chosen to match the image. Additionally, our dataset includes a wide variety of objects, surpassing those found in the custom Concept 101 and Dream Booth datasets. We also utilized various objects and background prompts during the training and inference phases, showcasing a broader range of objects and multi-concept combinations. This makes our dataset a more comprehensive tool for evaluating personalization tasks. Moving on to improving training time text prompts, we aim to design prompts that align well with the images in our dataset. We explored the best prompt designs for training and came up with some key strategies. One such strategy is the introduction of a global composition token, inspired by previous works like Dream Booth, which allows our model to describe detailed scene arrangements more realistically. We also repeated concept token prompts during training to ensure that each specified concept is present in the generated images, thus improving object persistence and completeness. Additionally, we incorporated background prompts to separate background learning from object identity, encouraging the model to focus on learning the object details. For evaluating personalization, we introduced two new metrics. The first, Composition Personalization Clip Score, CP Clip, assesses the accuracy of composition and personalization. The second, Text Image Alignment Clip Score, TI Clip, evaluates the model's generalization quality across different textual backgrounds, helping us understand the model's ability to generate new backgrounds without overfitting. We automated the evaluation process using a state-of-the-art model for open vocabulary object detection, OWLVIT, which can detect any object within our dataset. We then calculated the personalization clip score for each object detected in the generated images, ensuring that the number of objects detected matches the number of objects prompted by the text. This process helps us measure how well the personalized objects in the text are reflected in the generated images. We also calculated the TI clip score to assess the model's generalization ability, aiming for a score that maintains rather than increases, indicating that the model is not overfitting to the training set backgrounds. In summary, we've taken significant steps to enhance the training process and evaluation metrics for our MyCanvas dataset, aiming to improve the personalization and generalization capabilities of our model. Through careful prompt design and the introduction of new evaluation metrics, we believe our dataset provides a comprehensive tool for assessing personalization in image generation tasks. Section Summary. In this section, we present the dataset statistics of MyCanvas, which includes 150 objects with 41 probable compositions and over 10K images filtered down to 2,684 of best quality. Our dataset showcases a wide range of objects surpassing previous benchmarks like Custom Concept 101 and Dream Booth, making it more comprehensive for personalization tasks. Additionally, we introduce strategies to enhance training time text prompts by incorporating global composition tokens, repeating concept token prompts, and separating background prompts to improve object persistence and completeness in image generation. Section: Experiments. In this section, we delve into the experiments conducted to evaluate our methods. We start by discussing the baselines and implementation details. We chose to work with Custom Diffusion because of its reproducible codebase and its ability to be compared extensively with previous methods. We experimented with three different approaches. 1. Custom diffusion using individual source concept images. 2. Custom diffusion combined with our composed MyCanvas dataset. And 3. Our unique prompting strategy that builds upon custom diffusion with MyCanvas. For each approach, we trained a model and selected the best checkpoints for evaluation. We made sure to use prompts during evaluation that were significantly different from those used during training to better assess each model's ability to generalize to new, unseen backgrounds. We employed VIT-B32 as the backbone for both OWLVIT bounding box extraction and for calculating two clip-based scores, CP clip and TI clip, which helped us in our analysis. In our quantitative analysis, we organized the results by the number of objects in each composition. We used 41 different text prompts, with 6 samples per prompt for each composition, resulting in a total of 246 generated images. Our findings showed that custom diffusion's performance dropped by 50% when it learned with the original source images compared to when it used our MyCanvas dataset. However, when we applied our prompting strategy to custom diffusion, the carbon monophosphide clip score significantly increased. Importantly, the TI clip score, which indicates how well the background is generalized, remained consistent across all methods. This consistency ensures that the increase in composition accuracy we observed is not due to overfitting. For qualitative comparisons, we focused on the outcomes of using challenging and detailed prompts during inference. These prompts were designed to test the model's ability to generate concepts in new scenes, combine concepts with other known objects, and describe the relative positions of concepts. We compared the qualitative results under 3 settings. 1. Custom diffusion with the original source images. 2. Custom diffusion with our MyCanvas dataset. And 3. Our prompting strategy on top of custom diffusion with MyCanvas. Our strategy successfully separated objects that are similar in the latent space, which are often confused in stable diffusion models. Additionally, as the complexity of the composition increased, our prompting method ensured that all concepts were included in the generation process. We also found that using the MyCanvas dataset significantly improved the generation quality of existing personalization models like custom diffusion. In our ablation study, we evaluated the quality of 800 images generated by our Gen4Gen pipeline using a filtering tool. Each image was assessed based on the inclusion of personalized concepts, their appropriate placement, and the exclusion of visual artifacts, with rankings from 1 to 5. Only images rated 4 or 5 were added to the MyCanvas dataset. Our results showed that generating high-quality images is more feasible with fewer than 4 concepts involved. Additionally, we analyzed the effect of training data size versus the number of concepts. Our analysis showed that very few images are needed when training compositions with 3 or fewer concepts, but the training stabilizes between 10 to 50 images when there are more than 4 concepts. This indicates that our dataset size is more than sufficient for obtaining stable performance.